Okay, good afternoon. Let's start lecture. Okay. All right, so let's continue on the multivariable calculus. So now we're going to go back to the vector field now. Okay, so we have a new topic, which is called the greetings vector. Okay, so let's take a look at what is greeting vector. Okay, so let's start from very basic ones here. Let's say, remember, okay, if we are given a multivariable function, okay, so I'll use a function of three variables as an example. Okay, the x could be a function of a t, y could be a function of a t, and z could be a function of t too. Okay. So we learned in the previous lecture we can use the chain rule right here. So if I plug in x over here, y here, z here, the w will become a function of a t. So I can use the chain rule right here. The chain rule says partial f over partial x dx over dt plus partial f partial y dy over dt and dz over dt. Right, so that's your chain rule. Okay, so I'm going to manipulate this one a little bit at here, okay? Yeah. So basically what I'm going to manipulate this one, I'm going to rewrite this one into two parts here. See, this is partial f over x times this one times this times this. So I can basically rewrite this, okay, using the dot product, okay, of two vectors. And the first vector is partial f over partial x, partial f partial y, partial f partial z, and the other one here, dx over dt, dy over dt, and dz over dt. That's constant button noise, right? Don't know how to do that. Okay. Now here, if you look at this one here, then there are basically two vectors at here, right? If you look at the second vector at here, this is a function x of t, y of tz. So that could be basically the derivative of a parametric equation, dr over dt, right? So your parametric equation essentially is x of t, y of t, and z of t. And then the first one in here, this is something new. This is actually what we're going to define here. We're going to define, okay, a new vector here. Okay, so we're going to define a vector like this. It's inverted that triangle thing. I think I have covered a little bit before. So we're going to define this vector as partial f, partial x, partial y, partial f, partial z. So I'm going to define a new vector in here. Okay, so this one here. Now this is basically this vector here. Okay, sometimes we since short in a short notation, so we can write it like this. Okay, so this is essentially what we call the greeting vector. Okay, so this is basically the so-called greeting vector. Now, if you visualize in your head, so you have a function of three variables, and the the greeting vector here basically has three components in here. The first one is its partial derivative x, second one is y, third is z. If you have the function given, then you calculate the three partial derivative, then each one of the component will be a function of x, y, z, right? Okay. So if you plug in a specific x, y, z value into this vector here, then you get a specific greeting vector at a certain location. So basically you can see this is a greeting vector at point x, y, z. Okay? Yeah, so that's basically it's a vector at a certain point. Now here we introduced a new symbol added here. Okay, so this new symbol, so some notations here. So this guy, okay, this is an inverted triangle here. So this one here essentially is called del. Okay, so this is, you can call it a del. Okay, yeah, so you can read it as a del. Now, when you put this del and a function f together, okay, there are different ways you can call this. You can call, okay, so this you can read as a del f, or you can say this is a gradient of f. Okay, yeah, or just simply gradf. Okay, so that's what this del is. Okay. Now the del actually, okay, if you look at this definition of the greeting vector here, the del is actually, it's an operator. Okay, it is operator, and the operator is defined as partial this, partial y, okay, and partial over partial z. It's like a derivative operator straight d, right? So you apply this like a straight d here. You apply the d to a function f. You apply d to something else. That's an operator here. It's just same as that operator straight d. Well, except that this operator here, this is a vector, right? This is a vector here. So if you apply the operator to a function f, then the f comes here, 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 which gives you this greeting vector. Okay. So that's the greeting vector. So you remember the journey? I told you is from straight d to partial, and now we're at this stage, the del f now. Okay, yeah. So that's the journey here. So the rest of the courses we deal with this quite a bit. So basically, okay, yeah. So you'll see this operator very often. Okay. Now, in terms of the computation, you look at this one here. It's quite simple. If a question asks, what's a greeting vector function? And all you need to do is plug it in and calculate the partial derivatives. That's it. Okay. So let's look at a few examples. Okay. Before we move ahead, maybe just one more note in terms of the operator here. So if it is an operator like this, the derivative is an operator. So this one here it's also, should emphasize, on the linear operator. Okay, it's a linear operator. So what's the properties of a linear operator? What type property, David?
You can split up what's inside of it.
You can okay. Use the proper words that you learned in another course. Homogeneous, and the other one, additive. Together, you call it superposition. Okay. So basically, if you apply this operator to a function like this, then the superposition rule is satisfied. Okay, let's look at a few examples here. Okay, yeah, and we'll try to gain some in-depth knowledge into this greeting operator. But let's just simply look at a computation. Okay, nothing else but a computation. Let's say we have a function given. Okay, so here is a function with 3 variables given, and we want to find out the grading vector, and also we want to find out the grading vector at a certain location. Okay, this is a very procedural, really no trick at all. Apply the formula. Grading vector basically means you calculate 3 partial derivatives, and then you put it into this vector. And apparently it's quite straightforward. You have the w given in here, so the first partial derivative with respect to x, you treat everything else as a constant. So the first one 2x, then the last one is z over x. Right, so that's your first part. Second part, partial derivative y, everything else is constant, so only this term is y, so 2y. Last term, partial derivative is back to z, so negative 4z, and last one here, ln x. So that's the 3 partial derivatives, okay, for this grading vector. And we want to find a vector at the specific location 1, 1, 1. So what you can do is you just simply have to substitute the coordinates x, y, z into the grading vector here. So that will give me, so x is 1, z is 1, so that's basically 3, and then 2, and last one negative 4 plus ln 1 is 0, so negative 4. Okay, so that's the vector. That's the grading vector at that one particular location. Right. And I'll actually explain a little bit about how you interpret the grading vector and how do you sketch a grading vector, essentially. Okay. Okay, so let me give you another example right here. So this example is a function of 2 variables. So this function is 3 variables. When you have a function of 3 variables, the grading vector gives you as a 3D vector, right? So it's pointing to a direction in a 3D space. If I have a function of 2 variables, let's say z equal to f of x, y, let's give you the function here, which is x squared minus y squared. Right. Now, if you recall in the previous lecture, when you have a function like this, x squared minus y squared, now so if you remember, basically this is a saddle space surface, right? So when you have a function 2 variables, then you are able to visualize it or sketch that in the 3D space, which is a surface. In this case here, this function will represent the saddle surface, so that there's a point, could be either minimum or not, neither is a minimum or maximum. Okay. So let's calculate similarly. Let's calculate the del f, and then let's calculate del f at 1, negative 1. Okay. So let's calculate both of this. First, calculate del f and 2x, negative 2y. Okay. That's very, very simple. And del f, you calculate this, plug in the xy value, we get what? 2, 2, right? Okay. Yeah. So nothing really challenging here. But what I want you to establish concept here is how would you sketch this grading vector? Okay. Yeah. And what exactly does it mean? Now, this surface, I can sketch the surface. Actually, I have the surface at here. I'm gonna probably pull the surface into here. So that's the surface, right? For a typical Make it a little smaller here. Okay, that's the surface. Now, how do I sketch this greeting vector here, huh? Yeah. First of all, forget about greeting vector. Let's just say you have a vector here, which is 2 and a 2. So maybe the first question is, let's sketch the vector 2, 2. So how would you sketch that? How would you do that? Let's say this is a plane vector here, right? So you basically find the coordinates 2, 2 at here, okay? Yeah. And then what do? You create the vector, right? Yeah. So this is basically this vector here is 2, 2, huh? Yeah, it's 2, 2. Yeah, that's right. Should write this way here. Okay. But for when you draw the greeting vector, so what you do is you don't draw it starting from origin. Okay, you're starting from origin. What you need to draw the vector is you need to draw the vector at the location 2, 2. So basically what you do is, so this is the vector you created here, 2, 2, right? Then you move this vector without changing its length, direction, just move this vector all the way to have its starting location at 2, 2 at here. So basically your greeting vector should be this one here. Okay, so that's how you draw the greeting vector, so that from at here and then draw it over there. So that's your del f. Okay, so vectors free, so you literally can put it anywhere. But for greeting vector, when you sketch, you need to sketch it so that the starting point is at the location that you calculate this greeting vector. It's okay? Yeah. So for example, if I relate to the surface at here, okay? Relate to the surface. It's a little bit more hard to see, but so for example, this is x-axis, this is y-axis, okay? At which we're drawing the vector at -1 location. So x is 1, y is -1, so somewhere here. So that location is literally is somewhere here, right? It's somewhere here. Okay. Yeah. The zero reference point is over here. For the z comes the zero reference, so it's this plane here. It's this plane. So maybe I should actually find it. It's kind of hard to tell, but it's going to be somewhere right on the top of it, right? Yeah. Okay. Yeah. Then you draw that vector, basically del f. Okay. It's very small here. It's really hard to tell. Yeah. Maybe it's this one here. Okay. Yes.
So does a unit gradient vector have any meaning?
Yes, it does. But in this case here, where we're drawing here is a unit gradient vector, just the gradient vector.
But then if the length of the vector is 1, would they all be located at like 1 center point?
But the length, this one is not 1, right?
Yeah, but if it is.
Yeah, if it is 1, of course, then all the lengths will be the same, right? Unit lengths. But you see the way I draw here, you see the gradient, those blue color, the blue arrows here, those are basically the gradient vectors. So they all have different direction and also different what? Lengths, right? Yeah. So actually I'll tell you what the length means, what the direction means, okay? But basically the point I want to make is at this stage, if you're asked to draw the gradient vector, so first stage, you find the gradient vector and find the vector at that location, and then find the vector if you draw regularly, vector, and then you move the vector to the location where you did the calculation, basically. Okay, yeah. Is that clear? Okay, very good. So fundamentally, basically, as you can imagine, right? If you have a function of, let's say in this case, 2 variables, and you calculate the gradient vector, so you can create a map, basically, a distribution of gradient vectors in this plane here, right? In the xy plane. Okay, yeah. In next few lectures, basically this is called a vector field. It's a field of vectors here, right? Yeah. And each one of the vectors actually has a meaning. Okay. As in this case here for the gradient vector. Okay. So that's how. Basically, this is how to sketch. Okay. This is how would you sketch the gradient vector. Now, let's take a couple more examples here, but this is basically a confusing point, and I find in the past when students deal with this grading vector here. So I'm going to give you one very simple function. Okay. So z equal to x squared plus y squared. Okay. Yeah. So this one here, if you recall that, what does this function represent? It's a function two variables, so it's a surface, right? And if you recall that, this one basically gives you a so-called what type of surface? It's a paraboloid. Right? It's a paraboloid type of surface. Okay. So if you sketch this out, then you get a paraboloid here. Okay. And that's this function. Okay. So now I'm gonna create a little bit confusion for you. Okay. So number one case, and I want you to calculate the grading vector del f at 1, 1 location. Okay, so calculate this del f at 1, 1 location. So you can do the calculation. That's fairly easy. It'll get 2, 2, right? So del f is 2x, 2y. Then you plug in the x and y value, you get the 2, 2. So that's the vector for this gradient vector here. Okay. Yeah. Now I want you to sketch this now, right? Let's sketch this one here. Okay, let's sketch this. There'll be two things to sketch, but you can try to sketch one very simple one. Just sketch the vector 2, 2, the grading vector 2, 2. Okay, only sketch the grading vector 2, 2. So how do you sketch? So this is x, y. Find the coordinates 1, 1. Okay, this is coordinate 1, 1, right? Yeah. And then you sketch a vector. So the vector 2, 2. So in this case, so if you just sketch vector 2, 2, it'll start from origin. But in this case here, we start from 1, 1, right? So that basically is going to be a vector pointing this way, huh? This is will be del f. Okay, that makes sense? Yeah. So, and then the next thing I want to sketch is this. Okay, so basically, usually you sketch these two together. So at 1, 1. Okay, yeah. What's the z value? 0. No. You plug 1 here, plug 1 here. Z equal to 2, right? Okay. So basically, if you go up to the surface, okay, here is x, y, z. Here's a z value, and that z value corresponding to 2, right? Okay. Yeah. Now, if you recall in the previous lecture, when we learn multivariable function, and I start with function two variable, and I draw the surface, illustrate different type of surfaces, right? And then after the visualization, I said, okay, then another way of visualizing a surface, which is to use the so-called what? Contour plot. Remember, right? Yeah. And the contour plot basically means if you have a function z equal to x plus y, so basically means you slice the surface by a different constant z value. Does that make sense, right? Then basically every slice will generate a contour, okay? And when you put all the together, it's a contour plot. And every slice, I should say, every slice generates so-called what? Level curves, right? Level curves. So in this case here, if I do the same thing, here at 1, 1, you have a z equal to 2. So if I slice, okay, if I slice this surface using a plane z equal to 2, okay, using the plane z equal to 2. So what would be generated by this slice of plane at here? You would get what? You would get a circle, right? Okay, and when you plug a 2 at here, 2 equal to x squared plus y squared. That's a circle, and the circle has a radius of root 2. Okay, yeah. Now project this circle. Okay, project this. Basically, this is a level curve. if you project this level curve into the xy plane, and guess what? That curve basically will go through this 1 point. Okay, so that when you project that circle into the xy plane, you get level curve and passing through this 1 point. Does that make sense? Yeah. Okay. So now, I'll make a point why I'm doing this one here. So if you're looking from the top, right? If you look from the top, so basically what you see here is you have a level curve, and the curve has a radius of root 2, and the curve passes through basically 1 point. Okay. And then your grading vector, and your grading vector is here, is del f, right? So that's basically what I just draw it here. Is it okay? Yeah. And next, I'm going to make a point here. Basically, the grading vector here is perpendicular to this level curve. Okay, it's perpendicular to that. So the level curves and the grading vectors, often in time you draw them at the same time. Okay, you can visualize the both at the same time. Okay. So for this case, it's actually quite easy to visualize. For this type of surface, you will skip slice, right? Each slice. So each slice will generate a circle, and all of the circles are centered around the origin, right? Yeah. And if you plot another grading vector, you can imagine all of the grading vectors actually like a reading lines pointing out of the origin, basically, right? Yeah. So that's what the nature of if you draw a field of grading vectors, and you'll see that's that case, right? Yeah. Okay. Yeah. So I have a drawing here. Probably I can bring in this one here. So that's what this one looks like. Is that good? Yeah, that's basically what let's see all the level curves and all the grading vectors set here. Okay. Okay. So the next thing I want you to do now is So let's look at the second case, huh? Let's look at the second case. What's the first case? First case we dealt with this, okay? Now second case, I'm gonna deal with this one here. I'm gonna let the w equal to z minus x squared minus y squared. Okay, so this is second case. What's the difference between this one now? So this is what? Function of 3 variables now, right? This is function 3 variables. Okay? Yeah. Okay, so if this is function of 3 variables here, but you can, before we carry out here, but if we let w equal to 0, so what does this one give us? It give us back this paraboloid here, right? Z equal to x squared plus y squared. Okay? Yeah. Now if you recall that when we learned multivariable function, if you're given function 3 variables like this, so you can sketch that in 3D, right? Like the function 2 variable, you can't do that. But there's another way to visualize it, to use the so-called what? Level surface, right? Level surface. So if this is function 3 variables, you let the w equal to 0, then you get this guy here. So this is basically one level surface for this function of 3 variables. If you let w to 1, then you get another level surface, right? Yeah, basically level surface along this surface, you get a constant w here. Okay? So that's, you can through the level surface try to visualize it, but you can't sketch that. Okay? Yeah. So the difference basically means I want to see the case 1, case 2 is case 1 we deal with it's a surface, and we generate the grading vector, okay, for this function f here, which is a 2D vector, okay, 2D vector. Now for this one here, is w is the 3D, w is the function 3 variables, okay, and now let's calculate, instead of the previous one, let's calculate del w, okay, del w. And then let's calculate the del w at 1, 1, 2. Okay, and we'll also try to sketch this del w just like we sketched the del f. Okay, so del w is this one here, and if you calculate its grading vector, which is partial w over partial x, partial w partial y, partial w partial z. Okay, so look at the w function in here, give us negative 2x, negative 2y, partial w partial z is what? 1. Okay, only one z there, so partial w partial z is 1. That's your del w. Now if I'm interested in the del w at 1, 1, 2 location. So all we need to do is substitute 1, 1, 2 into the del w. So 1 in here, negative 2. 1 in here, negative 2. The z is always constant, so it's 1. Such your del w at 1, 1, 2. Okay, at 1, 1, 2. Good. Okay. So last step, sketch this grading vector del w. Okay, sketch the grading vector del w. When we sketch the grading vector del f, so what did I do? I not only sketched this del f, but I also sketched what? The level curve, right? The level curve associated with the, so see here, this is the function f. Okay, I also sketched its level curve at which location? At this z equal to 2, basically passing through the points, right? Okay, so I'm going to do the same thing. I'm going to sketch this grading vector, but it's a 3D now. So not only am I going to sketch the grading vector, I'm also going to sketch this level surface that passing through this point 1, 1, 2. Okay, so you sketch two things: the level surface and the grading vector. Okay, passing then the grading vector. Okay, the level surface has to pass through this 1, 1, 2 here. Okay, so sometimes it's not easy, you need a computer sketch, but in this case it's not that bad, so I can sketch the level surface first. Let's say, for example, okay, so this is your level surface, w equal to 0, or z equal to x squared plus y squared. Is that good? Right? That's your level surface. And then you sketch this grading vector at 1, 1, 2. Okay, at 1, 1, 2, because 1, 1, 2 is on the level surface here, right? So 1, 1, 2, find the point 1, 1, 2 first. Okay. So let's say the point is over here. So this is 1, 1, 2 point. And then sketch the vector negative 2, negative 2, 1, starting from 1, 1, 2. Okay, starting from 1, 1, 2. Okay, so Um, if it's not so obvious, maybe you can sketch -2, -2, 1 first, and then move that parallelly to the point 1, 1, 2. So I guess let's try -1, -2, -2, 1 here. X is -2, y is -2, z is 1. So this is x, this is y. Okay. So x is -2, y is -2, z is 1. Okay. So that point, that vector probably is pointing inwards, right? Pointing into that back of the paper there. Okay. Yeah. And then we're going to move this vector without changing the direction and the length all the way up to this location here. So all the way up to here, and redraw that. Okay, like that. Okay. So that's going to be your del W, okay, at this 1, 1, 2 location. Is that clear? Yeah. So at this stage, okay, one thing I want you to bear in mind is, okay, sometimes the question asked is, you just be careful what type of grading vector this question is asking you. Is it asking you the vector is del F? Basically, is it the grading vector this one? Or is it the grading vector del W? So maybe the question given is the function z equal to x squared plus y squared. Okay, is that function. But you may actually need is either it's the del F or the del W. Basically, what you need either whether it's a 2D or 3D, right? So that's the fundamental difference here. What type of vectors that question is asking for. Okay, that's the idea I want to show you here. Okay. Given the same surface, you could be asked to find the grading vector del F, or you could be asked to find a grading vector del W. Okay, so that's the difference. Okay. What is the physical meaning of a grading vector? Right? What's the physical meaning of grading vector? And what type of information really does it give us here? Yes.
This is how the normal plane is changing at that point.
How the normal plane is changing at that. Very close. Yeah. Now I won't give you a proof at this stage yet. Okay. I'm going to write down a conclusion and provide you a proof when we finish the directional derivative. Okay. Yeah. So for now, I'm going to give you a conclusion as to what a grading vector is. So I'll just say what's the geometrical meaning of a grading vector. Actually, maybe you know what? Let me show you. Let me show you this one here. Maybe you will be able to figure it out even just by look at this one here. Okay? Yeah. So first of all, all the blue arrows to here are the grading vectors, right? Okay? Yeah. Now if you are, let's say, at this location and here, okay, and it pointing to this direction, okay, pointing to this direction. Now correspondingly, that point corresponding a value for this function f at this location, right? So the z equal to something. Is that good, right? Or f of x, y equal to something. Okay? Yeah. So now you have a vector pointing to that direction. And imagine that if you are somebody, basically sitting on the ground, and if there's somebody else, okay, sitting on that surface, okay, sitting on the surface. Now, if you're going to be the one on the ground, okay, which is you have the information x and y, right? Okay, so the guy at here has the information of the z. That makes sense? Okay. Now, if you're the one at the ground and you want the guy on the surface to go as fast as possible, what instruction would you want to give to this guy here, right? See, that's the question here. So I want this guy to climb as fast as possible. And then you have the information x, y here. So you have to basically give an instruction, right? Say which direction that you should go so that this guy here will climb as fast as possible. Does that make sense? Right? So if you're the commander, basically commanding army at here, so that's essentially the instruction, right? Yeah. So the instruction you see here, if you look at this one here, this surface, you want to climb as fast as possible. You probably don't want this guy to go sideways, right? And you want the guy to go in this particular case, go all the way up, isn't it, right? And then all the way up basically means you have to send out a new instruction for the x, y, which is probably actually going to be this direction here. So that direction happened to be this direction given by the greeting vector. Okay? So basically, this is essentially the geometrical meaning of the greeting vector here. Okay? It literally has two meanings in it here. Okay? Yeah. First of all, so maybe write down presumption. So greeting of a function f, okay, or greeting vector of f, okay. First of all, okay, it points to the direction of the greatest increase of function f. So it points to the direction of the greatest increase for function f. So I'll come back to the second part here, but let's go back to this diagram here, right? Okay, coming back here, what's the function f? This surface here is a function f. Okay, this surface is function f. So that greeting vector here, del f, which is a 2D vector, it gives you the direction such that the function f will have the greatest increase if you go into that direction given by the greeting vector. Does that make sense? Right, that's basically what the meaning, the first part of meaning here is. Okay, yeah. Very, very useful. Okay. So let me ask a very simple question here. If this is a del f here, right? If del f give you the direction, the greatest increase for the function f, then what does the negative del f give you? The greatest what? Decrease. Yes. Okay. Yeah. Good. So let's come back to the point one later here. Okay. Yeah. Second meaning, part of meaning. Say function del f here is a vector. So I touched upon the direction, right? The meaning of the direction part of the part of meaning for the direction. Then the other part is its magnitude. Okay. So the magnitude of this greeting vector del f, okay, will give you the rate of a change or rate of increase. Okay. Is that good? Yeah. Actually, when you see these two conclusions, I won't prove here, but I will provide you proof once we finish the direction derivative. When you see the two conclusions that are here, it actually should actually provide it should remind you actually something for a function of single variable. So the del f is very much similar to what concept? To a simple derivative. Exactly, right? It's a simple derivative concept. Except the derivative in that case will give you a scalar, but in this case give you it's a vector concept, right? Del f is a vector. Okay. As a matter of fact, this whole thing is all about derivatives. So that's 3D to partial to del. It's about derivative. Okay. So there is just a transition from a simple derivative to a derivative in the vector fields. Okay, that's it. But in terms of the the background, what it really means, it's still a derivative operation basically. Okay. Yeah. Okay. Now I do have the other figure here. So this one, so this is the figure here for the 3D here, right? Yeah. So I guess sometimes it's kind of easy to understand the gradients for a function of 2 variables. Now when it comes to function 3 variables here, right? This is basically, see now in this case here I sketched all the gradient vectors on the level surface z equal to the same surface, right? The same surface. But this time the gradient vectors is sketched, okay, on the level surface. But then basically this is wrong here, so this should be W. So basically all the blue arrows here, okay, are del W. Okay. Now if you use a similar concept, gradient vector points to the direction of the greatest increase from the function. And then in this case here, all the del W, right, will point to basically point to the direction of the greatest increase for the W, okay, for the W here. Okay. So W is this one here, right, is this. So if this is one level surface, so this is a level surface, this one here is the level surface at a W equal to what? 0, right? W equal to 0. So you could have another level surface is W equal to 1, W equal to 2, okay? And that's essentially like the direction of increase of the for W, isn't it, right? So if I wanted to know how that increase, you see the arrow direction here, basically that points to the direction of the next level surface essentially. Okay? Yeah. That's slightly hard to imagine than the 2D case, right? 2D case. Okay. There are a couple more things I want to illustrate later, but there's another way of illustrating this concept is also quite straightforward here in terms of gradient vector. So we all love to eat the Filbert's, the doughboy, right? So let's suppose you have a very fancy oven. Okay, so how fancy it is? It's not actually gonna give you a time, but also gonna spits out a vector. Okay, it spits out a gradient vector. So that gradient vector basically will tell you where, which direction will give you the maximum increase in the temperature, so that you can cook it as fast as possible, right? So basically you put it into here. If it spits out a vector 3, 4, 5, for example, at this location, then you're supposed to move that yummy cookie to the next level, given by this direction. 3 steps to the Y, 4 steps from Y direction, 3 steps X direction, and 5 steps in the Z direction. So that's basically what it means, so that you can reach the maximum, not really the maximum, reach the next level highest increase for the temperature. Is that good? So let me ask you a simple question. What if this? What if the oven spits out is a 0, 0, 0? What is it? Yes, right? So basically there's nowhere to go, isn't it, right? There's nowhere to go. If there's nowhere to go, that means it's either at minimum or a maximum. So we don't know, right? Yeah. So that's actually the next step we're going to learn, the minimization and maximization for a function of multivariables. Okay, and the gradient vector. Okay, plays an important part of the tools to use to find that location essentially. Okay, it's the same idea. Remember that the derivative concept. When you have a function single variable, you draw a curve, right? And what's the nature for the minimum and the maximum location. The derivative of that location equal to 0, right? Equal to 0. Okay? Yeah. It's the same point. Okay. Okay. Now this portion in here, really, I see is the operation wise is very straightforward. It's more just to very well understand is what the grading vector means here. Okay. Yeah. So. And I often tell my students, when you take a class, you don't actually have a luxury to remember every part of the class. You probably forget the most of the class after 1 month or even just 2 weeks. Okay, but there's always a couple of things that you will remember for the rest of your life. Okay? Now, if I want you to remember one thing from this class, this is number 1. So, what's the physical meaning of a grading vector? That's it. Right? Yeah. So if somebody asks you a question during the interview, can you tell me what a grading? That's hardly impossible. What's the meaning of a grading vector? So then you can tell them that, right? Yeah. Okay. Okay. So let's continue at it here, and a couple of things relate to the grading vector thing. Okay. Yeah. So I probably will call them theorems here. So the first one here, I'll at least illustrate this and try to provide you a proof. Okay. So I'll mostly, in this case here, I'll separate the case to function 2 variable, and also separate the case to function of 3 variables. Okay. So let's say if I have a function in 2 variables, z equal to fxy, then if you calculate this grading vector del f, then this del f will be perpendicular to the level curve f of xy equal to c. Okay, it will be perpendicular to the level curve. And it's equivalent to see this statement, okay, as it's also perpendicular to the tangent lines, okay, of level curves f of xy equal to c. Okay. I kind of draw it and just tell you, right? Remember that paraboloid? You draw a level curve, and you draw the grading vector. Okay. So level curve is the circle, and level grading vector is a vector. And that grading vector is perpendicular to the curve. So let me provide you a proof at it here. Okay, so why is it perpendicular? Okay. So let's say I have a function of fxy. Okay. So if you have a function z equal to f of xy, then it's a surface, right? Then when you slice the surface, so you get a whole bunch of level curves. So this is basically, let's say this is one level curve. So it's one level curve at I don't know, z equal to c or z or f of xy equal to c. Okay. So this time you should try to visualize that function f of xy is on the top of this, right? So I only draw this in the xy plane, but this one here, it's a 3D surface. It's on the top of this this level curve here. Okay. Now suppose what it really generates a curve. Now suppose maybe the whole curve, or even just a part of the curve, you can describe that, okay, using a parametric equation r of t. Because it's a curve in 2D, right? So you can always describe that using a parametric equation r of t here. Okay, yeah. Okay, so my r of t, okay, could be some kind of a parametric equation. Okay, yeah. Now I'm gonna manipulate something now. Okay, I'll start from my level curve here. So this is the level curve, right? It's a level curve. Okay. So this level curve here, and this x and y, okay, are part of this parametric equation. So basically I can replace x with x of t, replace the y with x of t. Yeah. So you have a, if it's a circle, then x is a cosine t, y equal to a sine t, right? Yeah. So now I'm gonna do is I'm gonna take a derivative of both sides of this equation in here. So take a derivative, take time derivative here. Okay, so take a derivative of both sides of this equation. This side is constant, so that's basically going to be 0. And this side here, you take a derivative back to x, so that naturally give us, basically it's the chain rule. Okay, so basically give us chain rule. Then on the left side, I can rewrite it, okay, using vectors. So it's the vector this and dot this. Okay, it's this dot this. So now you can see the first part is basically what? The gradient, right? The gradient del f. And then the second part, this dx over dt, dy over dt, is basically the derivative of the parametric equation. The dot product of these two, 0. Then basically means the two vectors must be perpendicular. Okay, so must be perpendicular. That make sense? Yeah. So now you go back to the graph right here. If I pick a point on the level curve at here, for example, over here, okay? Yeah. First thing maybe I should draw is, if I draw, first I'll draw dr over dt. Okay? So dr over dt. dr over dt is a tangent vector, so that's tangent to the level curve. Okay? And then you draw the del f, and del f is perpendicular to the dr over dt. Right? So that's essentially prove the first part, prove the part A theorem here. The del f is perpendicular. So when del f is perpendicular to the tangent vector, so we would call that it's perpendicular to that level curve. Okay? Or if you draw, what you draw instead of a tangent vector, which what you draw here is a tangent line through that point, then the del f will be perpendicular to this tangent line, right, of this for this level curve at that location. Okay, yeah, good. So that's actually an important conclusion. So we will make use of this when we try to prove the mean and max, or when we try to find the mean and max for certain functions. Okay, yeah. Okay, so let me let's take a look at a very simple example here. We tried this already. Let's see that example. Maybe just look at it a little bit more here. If you have f of x y equal to x squared y squared, then you can calculate del f, which is 2x 2y. Okay, yeah. For a level curve, it's for a level curve f of x y to c. Give us x squared plus y squared equal to c. So now if you plot these two things together, first this one here is the level, this one is the level curve, which is a circle. Okay, that's a circle here. So different value of c will give you different radius for the circle. Okay, then del f 2x 2y, and you can literally see that basically it's going out of the way. All the way out of the origin there. Okay, so if you draw basically tangent lines to the circle here, okay, so that del f is perpendicular to the circle, right? Yeah. Okay, so that's the idea essentially why the first part of the theorem, del f is perpendicular to level curves. Okay, and also you can see that it's perpendicular to the tangent lines for the level curves. Okay, and that's the case when we deal with function of two variables, f of x, y. Okay? Now, if I give you a function of 3 variables, okay, so w equal to f of x, y, z, then we can have a very similar conclusion at here as the part A. Then the del f at here, okay, is perpendicular to the level surface, okay, f of x, y, z equal to c. Or we can see that this del f is perpendicular to the, so instead of a level surface, we see this tangent planes of the level surface. F of x, y equal to c. Okay, yeah. Very similar conclusion. Right? The tangent line is replaced with tangent plane. Level curve is replaced with the level surface. Right? Yeah. So how do I prove this one here? Show you a proof at here. Okay. Yes, very simple proof. Actually, similar way of proving it, like we presented. Okay, so let's say I have a function here. Okay, so given, let's see, a function f of x, y, z, okay, and a level surface So if you're given this function 3 variables and an arbitrary level surface f x, y equal to c. So once at this step here, as I said, you can visualize it. But once you're at this step right here, and you can always try to solve for the z in terms of x and y, right? So you basically always express the z using x, y. Okay, that's called explicit. Even though even if you can't, you still can have an implicit. So this one here, basically, you'll be able to sketch this now. Okay, so this is a surface, so you can sketch this. So whatever does it look like, so maybe it's just the arbitrary surface. Okay, yeah, so this one here is f of x, y, z, okay, equal to c. Okay, so that's your level surface. Good. Now let's visualize the next thing here. If you have a level surface like this, and then you can basically say, okay, I can construct a different basically curves along the surface. So I could really have so many different curves. You can have infinite number of curves, okay, going along that surface, right? So infinite. Okay. Now suppose that I can use a parametric equation to represent all the different possible curves, okay, on the level surface here. Okay, so that would be the r of t. So this could be r of t here. Maybe this is r1, or maybe this is r2, right? So who knows? Okay, yeah. Okay, so now let's start manipulations now. Okay, based on this concept. So we start from this level surface f of x, y, z equal to c. So this surface contains many parametric equations, or many curves. All the curves, basically, they are all on the surface, which means the x of t, y of t, z of t will satisfy the equation describing this surface. So the f of x, t, y of t, and z of t equal to c. Okay? That makes sense? Yeah. So then I will do the same thing. I'll take derivative of both sides. Okay? Take a derivative of both sides. Okay. So then this is a constant, so that's going to be 0. And for this side here, like what we did previously, it's a chain rule basically, right? And you end up with fx dx over dt, fy dy over dt, and then fz dz over dt. Okay. Yeah. So here I can rewrite this one using two vectors. The first vector is fx, fy, fz. Second one is dx over dt, dy over dt, dz over dt equal to 0. Okay. First vector is basically the gradient, del f. Second vector is basically the dr over dt, right? Equal to 0. So dot product 0 meaning the gradient is perpendicular to the tangent vector for this parametric equation. Okay. So coming back to the curve here. So let's say for this same location in here. So we could have multiple curves passing through this point here, right? All of the curve can be represented maybe using a different parametric equation. But it really doesn't matter whichever the parametric equation. It has all proved that the del f will be perpendicular to its tangent vector. So if I have a tangent vector to here for this red one, if I have a tangent vector to here for the black one, okay? What's the commonality? That del f is perpendicular to all of the tangent vectors. Does that make sense? Yeah. So imagine, right? If you have a surface at this location, how many tangent vectors would you be able to draw out of this location? Infinite, right? But then there's only what? One gradient vector. So that one gradient vector is perpendicular to all of the tangent vectors. So I can equivalent to see if at this location, if I create a tangent plane, right, to that point, to the surface, then the del f will be perpendicular to what? To that tangent plane. Does that make sense? Yeah? Good. So that basically proves this portion here, okay? Or this one here, the same thing. Okay. Now, there are quite a few different type of application now. So let's say I'll give you one example in here, okay? Okay, so find 244. Yeah, 244. Yeah. So find the tangent plane to this surface at this location 211. Okay. So the first thing I guess you need to try to visualize is when you see this one here, you should convince yourself there's going to be some sort of surface here, right? Yeah. It's not as straightforward as a z equal to x squared plus y squared. So it's actually implicit. So x squared plus y squared minus z squared equals 4. It's just some sort of surface, okay? Yeah. And we want to find a tangent plane to that surface at the 211 location. And the next thing you have to verify actually is this 211 on that surface or not? If it is not on the surface or not on the surface, there's actually probably something wrong with this question, right? Yeah. As a matter of fact, one of the midterm questions back several years back, and asking students to find a tangent plane to a certain surface at a certain point, and I didn't verify this point here. That point is not on the surface. So nobody actually questioned it. They just kept on calculating, right? You will still end up with something, but it just basically means nothing. Yeah. So that's the first step, actually, for me to verify is that point is on. So if you plug x equal 2, 1, 1, so 4 plus 1 minus 1, so it's on that surface, right? Okay. How do I find the tangent plane? So back to the same point. How do you find a plane equation? You need the point on the plane. You also need what? A normal vector to the plane. And we just proved that a candidate normal vector to the tangent plane is the grading vector. So we just need to find a grading vector for this surface right here. Okay, for the surface. So what you need to do is define a function's 3 variables here. Okay, so that's your function's 3 variables. Then when you let's call it w. When w equal to 4, then you get your level surface with level surface, which is this surface here, right? Which is this surface. Okay. So now the grading vector here. This paint's not working. So grading vector del w calculated equal to 2x, 2y, negative 2z. Then the grading vector at 2, 1, 1. So plugging x, 4, 2, negative 2. Okay. Alright. So once you get this grading vector, so that'll be basically the normal vector that you will use to create this tangent plane. So the tangent plane basically is 4 times x minus the point 2, 2 times y minus 1, and then negative 2 times z minus 1. Okay. Simplify this a little bit, you get 4x plus 2y minus 2z equal to 8. And then you can divide it by 2 on both sides, so 2x plus y minus z equal to 4. Okay. So that's your tangent plane to this level surface. Good? So I want you to try yourself another question here. So basically, if this is the surface, if this is a 2, 1, 1, then you can create this plane, right? Which is this one here. Okay. Okay, can you do yourself like this? So this is del f. Can you find a normal line? Okay, let's see. Just call it. Can you find a line? Okay, normal to the surface at 2, 1, 1. Okay. So try to do this very simple. Okay, is that good? Yeah. Okay. So I have one more point to illustrate, then we can call it here. Okay. Okay, so back to this theory here. So del f is perpendicular. So del f is perpendicular to the tangent planes, okay, of the level surface right here. Okay. Yeah. So I wouldn't call example, but let's just see here. So let's see if I have a function here. Okay. So if I have a function z equal to f of x, y. Now this is surface, right? This is some sort of surface. Okay. Yeah. And I can alternately I can see this. Here is the function of 3 variables, w equal to f of x, y, z. Okay. And then if I let w equal to 0, so we get a level surface. Okay. Yeah. So here's what we're going to try to find. Can you find the tangent plane? Okay, the tangent plane to z equal to f of x, y, okay, at x, y, z, x naught, y naught, z naught location, for example. Okay. So it's a little bit of generalized type of question here. Okay, yeah. So basically, at this location here, x naught, y naught, z naught, what will be the tangent plane to that location? Okay, yeah. Okay, so I'll follow the same approach here. In order to create a tangent plane, I need to find this greeting vector here, right? The greeting vector perpendicular to this surface. Now, the greeting vector here is not del f. The greeting vector here is what? It's a del w. Okay, so del w. So we need to find a del w first at x naught, y naught, z naught location. First, partial w, del w, okay, equal to partial w partial x, partial w partial y, partial w partial z. So what do we end up with? We end up with basically here's w here, so negative fx, negative fy, and then 1, right? Okay, yeah. So finally, substitute x naught, y naught, z naught, okay, into this del w. Okay, yeah. So then create your plane equation. So what will be the plane equation to create? It's negative fx at the location, let's say call it p naught here. Let's say this is a p naught. Then x minus x naught. Fy at the p naught location, y minus y naught. And z, here's 1. Z minus z naught equal to 0. So this is your tangent plane. Okay, this is your tangent plane here. Is that good? Yeah. So I'm gonna rewrite this slightly here. Okay, I'll rewrite it in terms of z. Okay, rewrite in terms of z. So what does the z equal to? Z equal to z naught plus fx at p naught and fy at p naught, like this, right? So this is your tangent plane. So before we finish today, you look at the last one here. What does that remind you? What does that look like? I think I covered this when we derived the total differential formula. So this is essentially what? The Taylor series expansion, right? The Taylor series expansion by keeping only the first couple terms. That makes sense, right? So basically, for this kind of surface, the tangent plane, it's the Taylor series expansion in the first couple terms. All right, so I'll give out another maybe assignments today, or I'm not sure. I have to look at it. Okay, so check out the connect. Right, maybe no assignments. Now remember, because the other section has no lectures for this week. Yeah. As a matter of fact, some student pointed out our section had 2 more lectures than the other section. Hopefully. So you will see some asynchronousness in terms of the tutorial, right? Yeah. So sometimes we go a little bit slower, trying to let them catch. Okay. But eventually we'll be actually faster than them.